Hello, everyone. Welcome to the first screencast for CSE 115 in this time of the coronavirus. Coming to you from still early on in Chapter 6. The slides are open to, let me see, slide 35 of the 93 slides in Chapter 6, Part 1. We're going to cover just example number 3, a game, in these slides. Let's just see how it goes. So when we left for spring break, we had just done the hats example as a way of simulating to find the probability that when a certain number of people toss their hats into the air randomly, the probability that at least one of them would pick up their own hat. We're going to try another little simulation example here involving a coin game. So say you're about to play a game and you're going to flip a fair coin twice as part of the game. And the rules are that if you get tails both times, you'll lose a buck. If you get exactly one head, nothing happens. If you get heads both times, you're going to win $2. Let's let capital W represent the number of dollars that you're going to win. So W is a number that depends on chance. That means it's a random variable. And I'm interested in what's the expected value of W. Okay? So in order to get purchase on this question of expected value, you really need to think about what are the possible values for W in the first place. Well, when you toss a fair coin twice, there's 4 things that could happen and they're equally likely. You could get tails and then tails, in which case W is -1. You get tails and then heads, and then nothing happens, so W is 0. You could get heads and then tails, and W is still 0. And then there's that one way to win money where you get heads and then heads, in which case you win $2, so W is 2. Now, since each of these 4 outcomes is equally likely, you've got a 1 in 4 chance of getting tails and tails. And so the chance that W is -1 is 0.25, 1 out of 4. There's 2 ways for nothing to happen, so the chance that W is 0 is 0.5. And then there's also a 1 in 4 chance that W is going to be 2. This is what we call the probability distribution of W. We know that through our intuitive ideas about probability. And you could write the probability distribution of a simple random variable like W using a table, where the first column, the little w column here, just represents the possible values of W. And the second column here represents the probability that capital W attains each of those little values, 0.25, 0.5, and again, 0.25. When you know the distribution of a random variable, then it's a lot easier to work with it. We'll see how that happens in our example. So thinking back again on Monte Carlo simulation, how might we do some simulations to estimate the expected value for W here? The good news is that the sample function is still good to use for a random variable like W where the outcomes don't all have the same probability. Here's the idea. We set up a little vector called little w that represents the possible outcomes, -1, 0, and 2. We set up another little vector that represents the probabilities of each of those outcomes. I'm calling it PW for probability of W. And then what we'll do is we'll sample from the little w vector some number of times that we want to simulate. And to keep it simple this time, we're just going to sample 10 times. Each time we pick a vector from an element from W, we're going to want to stick it back in so that things have that chance to be sampled again. But here's the key. for this application that's new. There is a parameter for the sample function called prob, and you can set it equal to a vector of probabilities for the outcomes of W. So I'm setting it equal to PW. And that's going to give each of the possible elements of little w to have the right chance to be sampled. And so in my example here, if you print out winnings, your results will vary from mine, but you're going to get a bunch of zeros and minus ones and maybe a 2, maybe. So think about prob when you need to work with little games where the outcomes don't always have the same probability. Hey, you always want to follow along, try out the code, vary it sometimes, see what's going to happen. I want to give you a little tip about that, not just press on through the slides the whole way. So I'm going to go to my RStudio, and here's a little trick for you. When you look inside the slides folder for our course, you'll see not only the HTML slides, but also the R Markdown source document that comes, that produces these slides in the first place. I've uploaded them for you. I'm going to go ahead and show you this document here. I'm going to pop it up big to take a look at it. There we go. And going to make it a bit bigger for you here. Okay. And you can always go to these, the R Markdown documents if you like, and it's a little bit more difficult to read them than the slides, but you can get used to that. There's a great table of contents down at the bottom, and you can use the table of contents to easily navigate around from one slide to the other. Those boldface things are the titles for the slides that do have titles. So it's pretty nice to use. I'm going to go back to example 3 again, but then I'll navigate down to what we call the code chunk in this R Markdown document that produced the code that we saw. And when you look through your document, you'll see these little code chunks in between the text. And those chunks, of course, are our code. And you can actually use this little arrow button to run that chunk. And you see the output. And so this might be a quick and easy way for you to work on and run examples. I think that if you do want to do this on a regular basis, you might want to save the R Markdown into your home directory somewhere. And that way you can actually make changes. You can change the code and see what's going to happen. So I'll do this. I'll work with this document in these slides. Okay, now back to the slides themselves. So if you wanted to estimate the expected value of the winnings, then you take that winnings vector and you just average up your winnings. You add them together, and the positive and the negative numbers cancel each other out a bit, and divide by how many there were, divide by 10. That can be done with the function mean. And in my winnings vector, the mean turned out to be minus 0.1. And so based on just 10 simulations, I would make the estimate that the expected value of W is minus $0.1, losing 10 cents a game on average. Of course, we really need to simulate a lot more times to get a better estimate of the expected value of this game. So we might say sample with size 10,000 instead of just 10. Same code as otherwise. And then when you try this out, you're going to get a result that is like what I've got here. I got 0.2391. You'll most likely come out somewhere near 0.25, about 25 cents per game on average. Now, in a simple game like this, I should point out that the expected value of the random variable actually doesn't have to be estimated just with simulation. It can actually be computed exactly. It's what we call a weighted average. This is not super important for the class, but I know that some of y'all will be interested in knowing this. What you do to compute an expected value when you know the probability distribution is to do a weighted average of the possible outcomes. You multiply each possible outcome by the probability of that outcome and add those products together. So like 25% of the time, you should be winning -$1. About 50% of the time, nothing should be happening. And about 25% of the time, you're winning $2. The sum of those things happens to be 0.25. That's exactly the expected value. So if you do know the probability distribution and the possible outcomes, and you have them stored in vectors as we do, then you could actually make R compute that exact same sum. Just say sum of W times P of W. You get the 0.25. Now, in the real applications that we make most of the time in this chapter, the random process is complex enough that these exact computations are difficult for people without a lot of probability theory under their belt, or they're even impossible to do, and so simulation will be essential. I want to bring up a side question. Suppose you could play that coin game many, many times. Would you want to do this? And to answer a question like this, you really have to consider what would your net winnings be. That is, you play a lot of times, you win 2 sometimes, you lose -1 sometimes, and a great many times nothing happens. But what's the total when you add the 2's and the -1's and the 0's together? Those are your net winnings. Would it be a lot? Would it be a positive number at all? Let's see. So one way to reason about this is to use the idea of expected value. Say that you had an opportunity to play this game 2,000 times. Now the expected value is 0.25, so on average you win $0.25 per play. So it stands to reason that in 2,000 plays, you should win about 2,000 times 0.25. That's 1/4 of 2,000. That's $500. So sounds to me like I'd like to play this game 2,000 times, as long as it didn't take too much time or effort. Another way to reason is to use simulation directly. Except instead of computing the mean of your winnings, just compute the sum. So here we have winnings as sample from our W vector. Size is 2,000, since we're going to play 2,000 times. Still replaces true, prob is just PW. But compute the sum of the winnings to find our net winnings in this simulation. And when I tried it here, I got 477. But you should feel free to try it a few times on your own, as occurs in these next slides. Let me remind you, back in RStudio, you could just find the appropriate spot, and you could try it yourself. So here's the code that produced that slide. I'm going to go ahead and run these 3 repetitions of summing up a winnings vector, and sure enough, I got around 500 each time. Okay. That's the end of today's little bit of slides. Next time, we're going to look at another simulation involving the chance of making a triangle out of 3 randomly produced little sticks. Bye-bye for now.